So yeah, my plan is just to, so you've got two booklets, right? Booklet 1 and booklet 2. And my plan is to spend the next hour and a half just working through them together. I do think this one is going to be a bit more challenging than the first one that we did. So it's good that you come along. We'll work through it together. Interrupt me at any stage if you have any questions about what I'm saying. So I went through it last night, so I've done the calculations already, so I can just save a bit of time there rather than mashing my calculator and that. But yeah, let's get straight into it. Oh, hey man, come grab a booklet there. Yeah, two booklets you need. So. Alright, so we've said first page should be some differentiation and possibly some integration. So we've got differentiate the following functions. Do not simplify your answer. So the first one we have is sine 2x plus cos 3x. So for us to differentiate this is, g'day boys, come grab the booklet here, up the front, on 903. Anyone else coming here?
Brad said he's going to be late, but
Make sure you can see forward. So this is sine of f of x plus cos of f of x. So we can just differentiate 1 second. 2 cos 2x, take 3 sine 3x. Alright, so derivative of cos of f of x is negative f dash of x sine of f of x. Alright, so that's the first one there. For the second one, we've got y is 2x on top of the square root of 3x take 1. Okay, so we have one function on top of another. We have u on top of v, so we need to use the quotient rule, right? U on top of v. So we've got u is 2x, u dash will be 2. V is 3x take 1 to the power of half. So for v dash, we're going to use the chain rule. We have a function to the power of n. And so here we have a question that's got quotient rule with chain rule involved in it as well. So that's going to be n f of x to the n take 1 multiplied by f dash of x. Now it says don't simplify, so you know we won't, and we're just going to smash all that together for the quotient rule. U dash v u dash v, take away u v dash, all on top of v squared. So just kind of grab a couple of bits here, Brad. Right, u dash v, take u v dash, all on top of v squared. Alright, on to the third one. We have e to the minus 2x multiplied by ln of 3x. So u times v, we have to use the product rule here. For instance, y equals. So we'll identify u dash, v, and v dash will be 3 on top of 3x, isn't it? When you differentiate ln of f of x, it's f dash of x on top of f of x. Now it can be simplified, right? That could be 1 on x. There's other parts of this that can be simplified. The 2's can cancel over here and so forth. And you wouldn't be penalised if you did, but I think the point of it is to say you don't need to simplify the answer. Okay, so then we're ready to smash that together to get the derivative. U dash v plus u v dash. All right. So then the next one is question B, and don't read it carefully. This is an integration one, right? It says find the integral of, we've got 2x plus 1 times 3x take 2 on top of x. Now at this stage, we can't integrate it, which means we're going to need to process it, manipulate it a little bit so that we can. So the first thing we might do is expand it, and then we're going to be able to cancel this x, right? So I'm just going to perform the expansion. So we're going to have at the top 6x squared, just using FOIL, take 4x plus 3x, and then take 2. And then we can collect here minus 4x plus 3x. And then I'll pause after this step. So we can collect. G'day guys, come grab a booklet. 907, look, Sam, 907. Grab a booklet. 6x squared take x back 2. Now we can simplify using index laws, right? So we're going to have 6x take 1, take 2 on x. Yeah, grab 1 of each. Just making sure my drink bottle's not in the way. Okay, so now it's in a stage where we can integrate that. We can integrate all of those components. This one here, I might just talk about this one by itself. We've got, so like when you're integrating, right, you're integrating term by term, just like we differentiate. So a good way to think about that one, you've got minus 2 on x, is it's minus 2 times the integral of 1 on x. That's a good way to think about it, right? And the integral of 1 on x is just ln of x. All right, so we can smash all this together. It's going to be 6x squared on 2, take x, take 2 ln x plus c. All right, so 6 is just hanging out. Integral of x is x squared on 2. Integral of 1 is x. We've said this can be written like that. And the integral of 1 on x is ln x. The minus 2 is hanging out the front. Don't forget to plus c. Alright, so the first page, we can anticipate some differentiation. We want to get them all right. All correct. You want to get full marks there. So, these out. Move that one up a little bit longer. Okay, question 2. Consider the function f of x equals the square root of x. Find the equation of the tangent at x is 4. So we've got a number of processes we could use. I'm just going to use y-intercept form. For a tangent, we need 2 things. We need the point of contact and we need the slope. And we've got the point of contact is x is 4. X is 4. We need the y value. And the function is the square root of x. Alright, so the y value then is going to be the square root of 4, positive 2. Next we need the slope. Alright, so we need 2 things for a tangent, right? We need the point of contact and the slope. So in order to find the slope, we need the derivative function. So if f of x is x to the half, then the derivative is half x to the minus half. Alright, so we'll put that in a form that's ready for us to sort of manipulate a bit. That's 1 on 2 root x. Okay, x to the minus half takes it to the bottom. And the half makes it a root, right? And we want to know what's the slope when x is 4. So we're finding f dash of 4. Alright, so you're not required to show all of these steps at all. Because all of that information you could get from the graph, right? You could go to the function square root of x, and you can g-solve the point when x is 4. It's going to tell you the y value, and if you've got the calculator mode set, it will also tell you the slope. Alright? Where that's not so useful is if it says find the slope exactly. It works in this circumstance, but it might not work if it's an irrational. G'day guys, come grab a booklet up here. Run out.
No, sure. I've got to.
Oh, no one else is allowed to come. We'll lock the door. I can print some more after. Okay, so anyway, we've got all the information we need. The slope is a quarter. So let's bring it together. We need the equation of a line that has a slope of a quarter and it passes through this point. So the equation of a line is y equals mx plus c. We got the slope is a quarter. And we've got when x is 4, y is 2. So we're going to plug that information in. We'll have 2 equals a quarter times 4 plus c. We'll get c is 1. Might just turn that meter off quickly. And I've got the one we did last week up here as well. Yeah. Thanks, mate. All right, so that's the first part of it, right? Find the equation of the tangent. Now, I want to say two things about this. Firstly, I did a lot of working out there, and you don't need to show all of that, but I'm just trying to be very clear because I'm presenting it to you guys, right? But you do still need to communicate, all right? So there's a couple of things that are essential. I'd say that. And then if we're going through here, you can go straight to there, and then you can go straight to there, and then you can go straight to there. You know, so you sort of only need those 4 bits of information. All that process I had initially, that was just me gaining this information, which you can get from your calculator, but you are working to show as well. All right, so we've got we've found the equation of the tangent now. So maybe I should just say as well, I probably should have said this before we started. So this is the MASA exam. So like it says in the logo there, that's a Maths Association of South Australia. So while they're not affiliated with SACE, it is run by maths teachers that do teach SACE. All right, so they've got a good idea of what's in the program. So really my only criticism of their exams is they don't give enough space, and maybe that's just because I write big. But yeah, SACE tends to provide a bit more space. Okay, let's move on to the next one. Show that the equation of the tangent at x is p. At x is p. So now we're doing the same thing. We're finding the equation of a tangent at x is p. All right, find the equation of the tangent at x is p, which means the y value is the square root of p. All right, and this is where having that slope function comes in handy. You can't get this one from your calculator. So we have the slope function was 1 on top of 2 root x. That's the slope function, which means the slope at x is p is 1 on 2 root p. All right, so we're finding the slope at x is p. We've got all the information we need there. So, equation of a line again, y equals mx plus c. We've got the slope is 1 on 2 root p. All right, so we're following the same process. Don't be alarmed by these p's. We're just going to treat the p as a number. Okay, then we've got, this is the point of contact we're going to substitute in. When x is p, y is the square root of p. All right, and again, I'm going to do this over a number of steps, just to really show very clearly what's going on. So here what we've got p at the top and p to the half at the bottom. All right, so I might even write it down. So we've got p and p to the half at the bottom. All right, square root of p is p to the half, and then there's plus c. So if we want to simplify that, what it's going to become is it's going to become p to the 1 take half, p to the half. All right, so that's just index ors. And don't forget the plus c. And what is p to the half but the square root of p? So we've got the square root of p equals half times the square root of p plus c. And from here you can see what the value of c is. But if you want, you can rearrange it. If we want to get c by itself, we're going to subtract half the square root of p from both sides. So what we have then is we've got root p, take half the square root of p, equals c. And you could leave it like that, I suppose, but these are like terms, right? We have one lot of the square root of p, take away half of the square root of p, we're going to be left with half of the square root of p. Okay, if you have 1 take away half, you've got half. All right, so that's the value of c. So then, the equation of this tangent, right, is 1 on 2 root p x plus half root p. And they've got a particular way that they want us to write it, don't they? So we need to collect them. If you look at how they've expressed it as a single term. Look, so it's one fraction, right? So we need to bring them together somehow. And so for us to take those together, they need to have the same denominator, all right? So at the moment, like let's express it like this, we've got x on 2 root p, and we've got root p on top of 2. So they almost have the same denominator, right? This one's only a little bit different. So to make it the same, we're going to multiply this one by root p on top of root p. All right, so we're multiplying it by 1. We're not changing its value. So then what have we got? We're going to have x on 2 root p plus root p times root p is p. Now they have the same denominator, we can bring them together. Alright, so I'm showing lots and lots of steps there. If you've run out of room, that's probably why. Just hit the right small one. I'm going to be writing lots of steps. Alright. A tangent to this same function has the equation of the line x takes 6y plus 9 equals 0. So this is in general form, right? Or it's general form, but it's been sort of rearranged a bit to move the constant over. Find its point of contact with f of x. So if this is the tangent, the question is, what is the point of contact? So there's a number of ways you can do this. I think probably the most intuitive way is to rearrange it to y-intercept form, right? So we're going to move the 6y over to this side. It's negative, all right, if we move it over, we're going to have x plus 9 equals 6y. And then we can divide both sides by 6. And so we've got x plus 9 on top of 6 equals y, right? So that's the equation of the tangent. And we want to know when does that meet the function. So we're going to say, when does x plus 9 on top of 6 equal the square root of x? Alright, and so you can graph those and just g-solve the point of intersection. Maybe I'll do that quickly. So x plus 9 on top of 6, and then the function square root of x, and they intersect here at 9 and 3. Alright, so that we need to state not just the x coordinate, but both. So maybe just make the comment, meet at 9, 3. Alright, so you get 2 marks for that, but there's one connection that I want to point out. And that is the relationship between, I'm just going to rewrite this, I'm going to take this here, that's the line we found, and write it over here, and see if you can see a relationship. We've got x plus 9 on top of 6.
PA system test, this is a PA system test.
And x plus 9 on top of 6 could be written as 2 times 3, right? Look at the relationship here. P is 9, and the square root of P is 3. Alright, and so what was our point of contact? 9, 3, x square root of x. Alright, so that's a link that we can make there, although this is probably a faster way of doing it. Excellent, let's move on to question 3. Any questions so far? Alright, so we've got a discrete random variable represents the amount of money in thousands of dollars. Alright, so that's, be aware of that, thousands of dollars. Earned positive. If it's positive, it's earned, and if it's negative, then it's going to be lost. That's what that part's saying. In an investment scheme over a period of time. And we're presented with the distribution. We've got x and the probability of the discrete variable taking on this event, -5, -3, m, 5 and 30. And then we've got the probabilities of these events occurring. 0.3, we've got k, we've got 0.15, 0.15 and 0.05. Okay, part 1 says find k. Find k. So find this value. So for it to be a valid probability distribution, all probabilities must be positive and all probabilities must add together to be 1. Alright, so you might just say sum of p equals 1. So therefore 0.3 plus k plus 0.15 plus 0.15 plus 0.05 equals 1. So we're going to take away all of that from 1 and we'll get k is 0.35. Alright, all probabilities add to 1, rearrange to get k. Alright, part B says find m if the expected value of this investment scheme is $300. So this is where you need to be a bit careful. Alright, because remember these events are in thousands of dollars. So if E of x equals $300, in terms of these numbers here, we're going to have E of x equals 0.3. Alright, because $300 is $0.3 thousand. So E of x is 0.3, and E of x is equal to each event times its probability. So let's work that out. We're going to have -5 times 0.3, -3 times k, plus m times 0.15, plus 5 times 0.15, plus 30 times 0.05, equals 0.3. Alright, so we've got numbers here. All of those we can add up, right? -1.5, what's that one going to be? -1.05, we've got 0.75. Anyway, so you add all of them up, and I got, when I did it, -0.3 plus 0.15m equals 0.3. Alright, so I've just added up the numerical components together. We're trying to solve for m, right? We're finding m given E of x is 300, 0.3. We'll rearrange, we'll get 0.15m equals 0.6. So we're adding 0.3 to both sides to eliminate this. And then we divide both sides by 0.15, and you get m equals 4. So for the expected value to be $300, we have to have m equals 4. Alright, part C. For what values of m will the expected value in this investment scheme result in a loss? Alright, so we have a loss when the expected value is less than 0. Right, that's going to be a loss. Okay, if the expected value is less than 0, we're going to have some loss. Alright, so down here we had a gain of $300, right? Down here we had a gain of $300. Now we're saying, what's the value of m if there's a loss? So this, we're going to take this component of it. Alright, we're going to take this component because we know the numerical parts add up to -0.3. And we have 0.15 is the probability of event m. And we're going to solve that inequality. We're saying, what's the probability of the expected value being less than 0? This is the expected value, right? So we're going to add 0.3 to both sides. And then divide both sides by 0.15. 0.15. Now when, so inequality works the same as an equal sign, except when you multiply and divide by a negative, then it flips, okay? So here we're dividing by a positive, so it remains in the same direction. Alright, so that's question 3. Excellent. Let's move on to question 4. Okay, I don't think I need to draw the graph of it, so I won't. Well, let's have a read. The graph of 2e to the 2e to the 0.25x is shown. Draw 4 rectangles that represent an underestimate of the area. All right, so that's your first part there. Draw 4 rectangles between x is 1 and x is 5. Underestimate. So that means they need to be below the curve. So here's our first rectangle, all right, from 1 up to there, and then across and down. All right, our second rectangle from 2 up to where it meets the function, across to 3, and then down. All right, so I'll give you a minute to sketch those in. And I might clear the board. So 2 marks just for drawing 4 rectangles, pretty good there. Part B, explain why this underestimate will be a better approximation of the exact area under the graph than the overestimate. Why is the underestimate going to be closer? So I'm going to provide a worded description for you, and this is going to be a bit of a link to our wine glass folio where we were looking at the Sharon. The function, right, the function is concave up. All right, so that's the first comment we're going to make. The function is concave up. Therefore, concave up. Now we need to specify, it's not concave up forever, but it's concave up over the interval, isn't it? Over the interval 1 less than x less than 5. And that's the interval that we're interested in. It's concave up over that interval. We can see that quite clearly. It's opening upwards. And so, therefore, there is less error with the underestimate. Alright, and let's illustrate that visually. Alright, so this is the point some of you guys made in the wine glass. Alright, so we're going to hyper exaggerate. Okay, here's the function concave up. This is the error associated with the overestimate. And this is the error with the under. And so we can see there is less error associated with the underestimate. Brad, can you see it all right? Some good real estate here.
No, right here.
Using a darker marker than last time as well. That blue was atrocious. Alright, calculate the underestimate, giving your answer correct to 2 decimal places. So for the underestimate, right, it's areas of rectangles, and we have 4 rectangles, and the width of each rectangle is 1. Alright, so if we consider the first rectangle, it's going to be 1 multiplied by, so we've drawn the rectangle up to here, and we need that y value. Now we shouldn't go and g-solve it from the graph, like you could do. That's going to take a long time. I think the most effective way is to just put in, like here's the function, right? It is 2e to the 0.25. Alright, so we want to know what's the y value when x is 1. So the first one's going to be 2e to the 0.25 times 1. Alright, the second one is going to be 2e to the 0.25 times 2, 0.5. And you can jump straight to that. The third one, 0.75, and the fourth one to 1. Now, I know you don't need to write the 1 out the front because we've got one already. You can even think of factorising it as well, but just for the sake of making the Alright, so then all you're doing in your calculator is 2e to the 0.25 plus 2e to the 0.5 plus 2e to the 0.75 plus 2e to the 1. Alright, and so you can evaluate that a fair bit rather than g-solving all of the values and then typing them in and adding them up together. Anyway, so I've evaluated this one. They want 2 decimal places. So I'm going to write 3 decimal places. That's 3 numbers after the decimal place. And round this one, it rounds up. Alright, it is possible to use more than 4 rectangles to estimate this area. As the number of rectangles increases, the area approaches a particular value k. Find the exact value of k. So they're just saying as the number of rectangles increase. So what's the exact area? Alright, what's the area approaching? So what that means we need to do is the integral from 1 to 5 of the function, right? 2e to the 0.25x. They want to know what's the area under the function exactly. So you can't just go ahead and calculate that in your calculator. We need to use the fundamental theorem of calculus and process this a bit. So the 2, you can pull the 2 out the front if you want. Let's do that because that's going to simplify our answer, right? 2e to the 0.25x. Now when we integrate e to the 0.25x, that's going to become, 2's hanging out, 1 on top of e to the 0.25x. It's 1 on top of 0.25. What am I doing? 1 on top of k. Alright? E to the 0.25x. That's better. From 1 to 5. So I have seen people in the past, like they go from here and then they sort of forget to integrate, or they go from here and they differentiate. Alright, so just make sure, do it slowly, do it carefully. Alright, and get it right. Alright, integral of e to the k is 1 on k, e to the k. Alright, so now we're ready to chuck those numbers in and process it a bit. The 2's just hanging out the front. We have now 1 divided by 0.25, that can be simplified. 1 on 0.25 is 4. Sam, all good? Yeah. So that's going to be 4, and we've got e to the 0.25 times 5. Alright, and then we're going to take away e to the 0.25 times 1. Alright, and so in the simplest terms, that's 8e to the 1.25, take 4e to the 0. Take 8, sorry. 8e to the 0.25. And we can't collect those in any way, they have different powers. You can leave the 8 out, you can factorise the 8, leave the number up front, doesn't really matter. Okay, very good. Let's move on then. Show by differentiation that the integral of x sine 2x equals a quarter sine 2x, take half x cos 2x. Alright, so they want us to show that this is true. Now you're not expected to integrate the product here, right? They want you to show it's true by differentiation. If you integrate this, you get this. Therefore, if you differentiate this, this is what we're going to obtain. So that's what we need to do. We need to differentiate this. So first I'm going to make that statement, d on dx of a quarter sine 2x, take half x cos 2x. That's what we're going to do. We're going to process that. Now here, we can do that component fine. Over here we need to use the product rule because we've got half x times cos 2x. So I'm going to make an argument there. We've got u Alright, so we need to use the product rule there for that. And now we're ready to bring it all together. So here, the quarter's going to hang out. The derivative of sine 2x is going to be 2 cos 2x. Alright, so that component's been differentiated. Then we've got to take away, and we're using the product rule for this one, right? u dash v plus u v dash. Alright, now I'll put that all in brackets because we're taking away that component which means we need to take away that negative needs to distribute. So that whole thing needs to be in brackets. And so we're not using any of those trig identities here, okay? So whenever they pop up in exams, they do provide them for you, so you don't need to know them. We'll talk more about that in the reflection of the trial exam, I think, because you'll see it pop up there. So you don't need to know the trig identities, but they do tell you substitutions you can form. We're not using any of those here, we're just going to collect terms here now. So this can simplify a bit, this negative is going to distribute. Let's go ahead and process that. Here we can simplify this as well. A quarter times 2 is a half, so we've got half equals 2x. We've got take half, oh look at that, take half cos 2x. Alright, and here we've got 2 times a half, so the 2's cancelling, and then we've got negative times a negative, so the negatives cancelling, and we're just left with plus x sine 2x. Alright, so you differentiate that, you obtain that, therefore, if you integrate that, that's what you obtain. So it's true. Okay. Explain why sine 2x from 0 to pi on 2 can be a valid probability density function. So for a valid probability density function, there are 2 properties. The first one is that the function has to be positive. Alright, that's because we cannot positive or equal to 0, we can have 0 probability. So greater than or equal to 0. We can't have negative probabilities occurring. And then the second one is that the integral over the domain of which the function is a valid probability density function equals 1. So they're the 2 components, 2 contingencies that the probability density function needs to satisfy. So why can sine 2x be valid? It satisfies both of these contingencies. So let's write that. It satisfies both requirements for a valid probability density function. Okay, now consider the continuous random variable x with probability function, alright, so the one we're talking about above. Part C, find the probability of pi on 6 being less than x being less than or equal to pi on 4. Alright, so for a probability density function, that means the area under the curve from pi on 6 to pi on 4 of the function that we're talking about. Now this is only, look here carefully, this is only worth 1 mark, so I'm going to be putting that in my calculator. Alright, it doesn't even say find it exactly, so it just says find it. So this is the statement I'm going to put in my calculator, and anyway, it jumps out with a quarter. Alright, so the probability of the event occurring between pi on 6 and pi on 4 is a quarter. Okay, part D. Write down an expression for the mean of x. So this is where you look at your cheat sheet, because you can't remember the formula. But the mean of a probability density function is the integral of x, f of x, over the domain for which it's valid, from A to B. And so in our circumstance, that's going to be from 0 to pi on 2 of x times sine 2x. Alright, so we'll mark there just from the formula. And they've been very generous here because they've said using part A. Using part A. And so sometimes they don't say that. Sometimes they say something like hence. Okay, so anytime you see hence, it means using what we've looked at before. You need to look up and to use something you've done. Using part A, find the exact value of the mean. So they want us to evaluate this. 0 to pi on 2 of x sine 2x with regards to x. So we know from part A that the integral is this. Alright, so that's the link that we're making. Okay? So we can jump straight to the integration step. We'll have a quarter sine 2x, take half x cos 2x. Alright, and let's get into processing it. So we're just going to sub in using the fundamental theorem of calculus. Alright, so the fundamental theorem of calculus, you've got the integral statement, you've got the integration step, and we can process it there to the answer, but it does want it exactly. So we're probably going to show some working out for our sake, rather than for the sake of the question. So I'm going to do a little bit slower, like this is an intermediary step, not a necessary step. That's a 2. Alright, so the whole right hand side is tending to 0. Sine of 0 is 0, so that component's going to disappear. Now cos of 0 is 1, but we have this 0 out the front. 0 times 1, that's still going to be 0 as well. So that whole right component we can disregard. And then over here, once we've simplified these a little bit, sine of pi. Alright, so again, you can use a calculator and so forth, but just think about it. Pi is here, and the y value is 0. So sine of pi is 0, so that component's disappeared. Cos of pi is minus 1. So what have we got? We've got minus half times pi on 2 times minus 1. Right? Cos of pi is minus 1. So the negative times the negative cancels, and we've got pi on top of 4. Alright, so that's the exact value of the mean. Alright, write down an expression for the mean of x, standard deviation of x. So the standard deviation of a probability density function is the integral from a to b of x squared times the function, and then take the mean squared. So that's the formula, alright? Now you need to make sure that the dx is here, so it's integral of that, and then take the mean. The mean does not belong inside the integral statement. So let's write that out for our purposes. Don't just write out the formula. They've said write it out for the mean of the standard deviation of x. So they're talking about a particular distribution. So that means for us it's the integral from 0 to pi on 2 of x squared sine 2x. With regards to x, take, and we've calculated the mean, pi on 4 squared. Alright, even if you don't have the mean, if you didn't calculate it, or if you didn't get it to, you can write here mean of x. Alright, that would be appropriate, because they would see that you hadn't obtained it in the first part. And then in the second part, find the standard deviation correct to 2 decimal places. So if you evaluate this, you get 0.116, which will round to 0.12. 2 decimal places. Alrighty. Small business makes and sells homemade biscuits. In order for the biscuits to have a homemade appearance,
This is the PA test. This is the PA test.
it's like an airport. They are manufactured in slightly different shapes and sizes, but it can be assumed that their weights are normally distributed with a mean of 25 grams and a standard deviation of 2.3. An investigation into the mean weight of the biscuits is carried out. We have a sample of 12. And the mean of the sample of 12 was found to have a weight of 24.5. Fill in the following boxes with the appropriate values to calculate a 90% confidence interval. Alright, so we have x bar take z alpha on 2 multiplied by the standard deviation on the square root of n. So that's the lower component, and then we're going to have the upper component here, right? So x bar is the observed sample mean. So from the sample of 12, we had a mean of 24.5. Alright? The value for z alpha on 2, we've got a 90% confidence interval. So I think we did this when we just did the last exam, how to calculate it. But what it is, we're saying, what are these numbers on the z distribution? What are these numbers? Such that this area is 0.9. So just to do a quick refresh, this is an inverse normal calculation. The area is 0.9. The tail is central, sorry. What do you need? Tail, central, mean and standard deviation. I haven't put them up here in the correct order. I can't remember the order they go in. But that's the calculation you're going to do to obtain these values of z alpha on 2. So you can do that straight from your calculator, alright, so pretty common ones they ask, 90, 95, 98, sometimes 99, occasionally others, but that's what they're asking, right? So that's how we obtain the value of z alpha on 2, and for our purposes here, it's 1.64, alright? So if you go ahead and do that calculation, you'll get 1.64. Okay, now we're going to multiply that by, and it's standard deviation on top of square root of n. So in the third box, they've given you a big box which suggests express this as a fraction, right? 2.3 is the standard deviation of the population. That's what we're told in the initial question. And divided by the square root of n, that's 12. Okay, so that's the lower component, and that's mirrored in the upper component of the confidence interval. Alright, so go ahead, put that in. And now it says calculate it, right? And for me, I'm not going to waste my time writing all this out in the calculator. I mean, you can argue it takes the same amount of time, but I'm just going to go straight to the stats menu for the confidence interval. And why that's going to be useful, that's going to be useful just in case I've made some sort of typo up here or something like that as well. So where's that? We go menu, statistics, confidence interval. Now we're talking about the confidence interval for a sample, aren't we? It's not a proportion, it's a sample because we're given a mean. We're given a mean. So that's interval z first sample. Interval z one sample. And let's write this information in. Our confidence level is 0.9. Alright, so even if you don't get the stuff above, like if you weren't sure what to write in the boxes, you can still obtain the confidence interval, right? You can still get these marks. The standard deviation is 2.3, the observed mean is 24.5, and the number of, the size of the sample is 12. Alright, so you don't need to write that out, by the way. You can, alright, you can, so that when you come back to check your working out, you can see pretty clearly what's the stuff that I put in my calculator to obtain this confidence interval. And that's a good idea to do. Anyway, so we do that, and this is what we get. There's our confidence interval. Alright, is there sufficient evidence to suggest that the mean weight of biscuits is not 25 grams? No. Alright, one mark for writing no, and then another mark for justification, because 25 lies within the confidence interval. So, no, as 25 grams lies in confidence interval. Alright. The company wishes to package 15 biscuits in a sealed bag labelled net weight 380 grams. Find the probability that the bags will be underweight. Alright, 15 biscuits make a bag. What's the probability that a bag of 15 biscuits added together is less than 380? So now we're talking about this, right? Probability of S15. the sum of 15 biscuits being underweight, being less than 380. So that's what we're going to calculate. This is a normal distribution calculation. So it's NCD, our lower boundary is minus infinity, our upper boundary is 380. And we want the mean and standard deviation of S15. So the standard deviation of S15 is equal to the standard deviation of X. So I might write this out. Standard deviation of Sn is equal to standard deviation of X multiplied by square root of n. And the mean of Sn is equal to n times the mean of X. Alright, so that's the distribution of Sn. So for S15, we're going to have here square root of 15 multiplied by 2.3. Now just be careful when you're writing that out, that in your calculator you don't have this sort of square root extending over both of them. It's the square root only belongs to the n. And so for that reason, it can be better to put the standard deviation first, right? 2.3 times square root of 15, just to make sure you don't have that issue. Okay, so watch out for that. And then for the mean, doesn't matter what order you write them in, we've got 15 times what was the mean of x. Now, here's a question, which one do we use? Do we use the 24.5 or do we use the 25? The answer is, does anyone want to say?
24.5.
No, we use 25 because the mean of x always trumps, always takes precedence over the sample mean, right? That's the mean of the population. So we're going to use the 25. All right, and so that's the normal distribution calculation that we're going to evaluate. You can type it out like this, you can type it out in the normal distribution mode. I've got 0.72. So that's pretty bad, right? 72% of bags are below the 380 grams. All right, so they're going to need to add some more biscuits in. So let's see. The company requires less than 1% of bags to be underweight. Determine the minimum number of biscuits required for each bag. So this one's just going to be best using trial and error. We're going to add more biscuits. So we're going to say, what's the probability of S16 being less than 380? What's the probability of S17 being less than 380? So you're performing this calculation, all right, until we get a probability less than 0.01. Alright, but it's not the same calculation, right? You have to change these. What are we changing? You're changing this number. So that's going to be 16 and 16. And so if you do it for 16, I got 0.015. Alright, so that's close. That's very close. Alright, so look, we went from 72% underweight. Now we've got 1.5% underweight, but it still doesn't satisfy this requirement. So it is going to occur here, right? We're pretty confident of that. And if you calculate this one, you've got 0.00001. So therefore, 17 biscuits. All right. 17 biscuits will give us net weight under 380. All right. So we're on to the second booklet. Now we've got two objects, A and B, move in a straight line. The displacement of object A in meters after t seconds is given by S of t equals 2t take 3 multiplied by ln of 2t take 3 take 2t. That's the displacement function. Valid from 1.5 to 4. Show that the velocity of A is given by this function. Alright, so the velocity is equal to the derivative of displacement, right? So we need to differentiate this. And in order to differentiate this, we should just use the product rule. Like, you can expand and distribute, but you're still going to need to use the product rule, right? We've got u times v. And for there, we'll just use simple differentiation. So we have u, 2t take 3. So yeah, u dash v plus uv dash, and then don't forget this part. You differentiate 2t, you get minus 2. And look at this, we've got 2 ln 2t take 3 here, and this is where we're going to simplify, right? We've got 2t take 3 at the top, 2t take 3 at the bottom, that cancels, and then we've got 2 take 2, that cancels. So we're left with v of t here. Okay, part B, find the exact time when the velocity of A is equal to 3 meters per second. So that means when our function here, 2 ln 2t take 3 equals 3. Alright, when is the velocity equal to 3? So this is a logarithmic equation that we're going to solve. So first we divide both sides by 2. And then to get rid of ln, we're putting e to the power of both sides. So we're going to have e to the ln equals e to the 1.5. And so here we're going to have 2t take 3 equals e to the 1.5. We will add 3 to both sides. We're solving for t, right? So we have 2t equals e to the 1.5 plus 3. And then divide both sides by 2. Alright, it does say exact time. If it didn't say exact, then that's something you could obtain from the graph, right? You could graph the velocity function and g solve what's the x value when y is 3. Alright, part C. On the axis below, sketch the graph of the velocity function. Clearly indicate any x-intercepts, asymptotes, and endpoints. Now, the only argument I really want to make here is about the asymptote. Alright, so again, we did touch on this in the first exam we did, the exam we did last time, is that ln of x will exist provided x is greater than 0. So that means this function here, which is 2 ln of 2t take 3, will exist provided this component, 2t take 3 is positive, 2t is greater than 3, t is greater than 3 on 2. T has to be greater than 1.5, so that's where our asymptote occurs. Alright? So when you sketch the graph, you can mostly refer to your calculator, and you can even get the asymptote from your calculator, although sometimes it can be a little bit fiddly to see. But there's an asymptote at 1.5, so x equals 1.5, and then it does something like this, right? The root you can get straight from the calculator, it's a nice clean 2. Yeah, that's what they're looking for, the shape, the asymptote, and the root. Alright, any questions about that so far? So yeah, referring to our calculator mostly, the only argument I wanted to make was for the asymptote. Alright, write down an expression for the distance travelled by the object from time is 1.8 to time is 4. Now, distance is area under the curve of the velocity function. Now, what this tells us, this is the velocity function, right, is we have negative velocity from, I'm going to put 1.8 there, alright, we've got negative velocity from 1.8 to 2. So that means it's moving to the left. So that means when we consider the distance, it needs to be the negative of it, alright, because it's got negative velocity, and so to calculate the distance of it, we need to make it negative. So that's negative 1.8 to 2 of the velocity function, which is 2 ln 2t take 3. Alright, so that's going to give us the area of the first component. Alright, and the other way you can think about it, right, it's below the x-axis. How do I calculate the area? Well, it needs to be the line y equals 0, take away the function v of t, which is how we get the negative 0 take function, and then we want the area from 2 to 4 of the function. Alright, and I think it does just ask for an expression of it, doesn't it? Write down an expression, so we don't need to evaluate that. Okay, part E. Find the exact value of the distance travelled by the object from time is 2 to time is 4. So now they're only interested in this component of it. Find the exact value. Find the exact value. Now, in methods, you're not required to integrate ln of f of x, okay? But we're given the answer to it, all right? So you're not required to use a rule to do it, I should say. But we're given what the integral is, what the antiderivative is, because we differentiated the displacement function. So 2 ln 2t take 3 goes to 2t take 3 ln 2t take 3 take 2t. All right, that is from the first part of the question. And so this is where it's a little bit more sneaky, right? Is they haven't said using part A, right? They haven't said that. So it's up to you. How am I going to solve that? Let's look back. What have I done here? What have I shown? Okay. So that's what we're from 2 to 4. All right. So let's write this one out using the fundamental theorem of calculus. We're going to have 8 take 3. So these ones, right? I might do these ones a little bit quicker rather than writing the whole thing out. But 2 times 4 is 8. Take 3 is 5. So I'm going to have 5 ln 5. All right. Take away 8. All right. So that's when we put in 4. And then let's take away when we put in 2. We're going to have 1. That's 4 take 3. 1 ln 4 take 3. 1. And we know ln of 1 is 0. Alright, so that part's going to be 0, and then we have here take away 2 times 2, 4. Alright, so that component 0, we have 5 ln 5, take 8, take negative 4, so that becomes plus 4, 5 ln 5, take 4. Alright, minus 8 plus 4, minus 4. Okay, the other object has velocity function. So the velocity of the second function is ln of t squared. What transformations would map the graph of v of b onto v of a? Ooh, what transformations? So here we're talking about moving the function around. So don't fret about this. This is just that 2 that can come right at the front. This is just 2 ln t. And we're saying, how do we get from 2 ln t to 2 ln 2t take 3? Alright, how do we get from here to here? Now there's 2 ways you can answer it, right? The minus 3, that's a horizontal dilation, right? And the 2 is going to be a vertical dilation. But I think there's a simpler way to think about it for us to answer. And that is, if we look here, one way we can express this is 2 of ln, 2 times t take 3 on 2. Alright, if that were to distribute, you're going to obtain what we had above. Okay, and the reason I've done that is because now we've got ln of a b, right, which is ln of a plus ln of b. So we can split this, right? Here's a, and this second component in brackets is b. We can express it like this: 2 ln 2 plus 2 ln 2t. T take 3 on 2. All right, and now I think it's much clearer, the transformations that take place. All right, I think it's much clearer because this is a number and it's just moving it up or down. All right, so shifts up 2 ln 2 units, and now here we've got the horizontal translation. Negative 3 on 2 moves it 3 on 2 units right. I think the best way to understand it is to make the algebraic argument, right? Nonetheless, you might be able to see it on your calculator. All right, definitely you should get the mark for the horizontal translation. So you might say something like move 3 on 2 units right. But you can make a case for a vertical dilation or a vertical translation. Both of those are correct. I think this is a better one to say. Up to ln 2. Alright, so that's we should be able to get that mark. This one's a little bit trickier to get. Okay, any questions about that? And so what I mean by using your calculator is, even if you were to graph this function and graph the our velocity function, if you're graphing both of those, you're saying, what do I need to do to move this one onto that. How do I move it? How am I going to move it across and up? Okay? And you can experiment around, right? You can fiddle around with it, changing some of the values and so forth. Alright, well, we're good at that because we've been doing that with the wine glasses and so forth. Okay, so that's that part. Find the point of intersection of the graphs. So we're saying, when does 2ln 2t take 3 equal, so they give you ln of t squared, and if that's what you've got, that can be a little bit tricky to answer, okay? But if we pull the 2 out the front, it makes it much easier, right? If that 2 is here, we can divide both sides by 2. Alright, and here, you don't even have to perform the e to both sides because ln is a function, right? And so it's like saying, you know, if you have the square root of a equals the square root of b, a has to equal b. It's a function. If you have sine of a equals sine of b, then a has to equal b. So that means the inside component here, 2t take 3 has to equal t. We'll solve for t. I'm going to move this t over here. So we'll have t, and then move the 3 over. We've got t is 3. And you could even obtain that by g-solving the point of intersection, right? Alright, and then last part, sketch the graph of VB on the set of axes provided, and they've given you a domain. So this one has an asymptote at 0, so you get a mark there for putting the graph on, showing the point of intersection, right? They want to see the point of intersection. So, alright, we're doing well. We've got 2 questions to go. 3 questions to go. Okay. Let f of x equal the square root of 2x take 3 for x is greater than or equal to 1.5. The graph is shown below. Let a be a fixed point, 6, 3, and b be any point x f of x. On the graph above, draw the chord AB when A is placed at 8 f of 8. So I'll skip ahead to this question and I'll show you where the line is that you're drawing. Alright, so you're going to plot point B at 8 f of 8. So it's going to be there where my cursor is now, right here, and then you're just going to draw a line connecting them. Alright, make sure it's clear that you can see it, do it dark, so you get the marks there. For this position, find the slope of the chord AB correct to 4 decimal places. So the function is, right, the square root of 3x, 2x take 3. Now slope is y2 take y1 on x2 take x1. That's the slope function. So we know the coordinates of A. So A is 6, 3, and we need the coordinates of B. We've got B is 8, the x coordinate is 8, and the y coordinate is the square root of 2 times 8 take away 3, so 2 times 8 is 16, take away 3 is 13. So they're the coordinates of B, which means the slope is square root of 13 take, I haven't written that one up properly, that's 9, no that's right. Square root of 13 take 3 on top of 8 take 6. So that's what they want you to evaluate. Correct to 4 decimal places. So that's going to be 0.3028. Okay, the following table shows the coordinates of the fixed point A and the various coordinates for the point B. Fill in the 2 missing values for the slope of AB. So B is getting closer and closer and closer to A, right? So we're going with, what about when the coordinates of B are 6.1 and 3.0332? So in that circumstance, I'm going to just do the first one here. We're going to have 3.0332 take away 3. Y2 take Y1 on top of X2 take X1. Alright, so that's going to become, I'll simplify it, but you don't need to. 332 on top of 0.1, and we've got 0.332. And then if you do the next one, we're going to have 0.0033 on top of 0.01, and you get 0.33. Alright, so we've gone 0.3028, 0.3166, 0.332, 0.33, and they're saying, what is it approaching? Okay, as point B approaches the value of A, the slope approaches some limiting value K. Make a conjecture about the value of K, expressing your answer as a fraction. Might be difficult to see. Alright, might be difficult to see. Let's pretend we can't see it, and let's go ahead and prove the conjecture, and then we can go back and answer that part. So maybe you can see it, maybe you can't, we're not really sure what to answer there. They're saying, what fraction is it approaching? Alright, so it's getting quite close to a fraction. So, using first principles, prove the conjecture. So they're saying, using first principles, what is the slope, what is the instantaneous slope at point A? So here we go. First principles for this function, square root of 2x take 3. Okay, f of x plus h. Alright, x plus h where the x is. Take away f of x on top of h. So set it up, get a mark there just for writing the first one. Now, whenever we have a square root for first principles, we're going to need to multiply it by the conjugate so that we can use the difference of two squares, right? So we're going to multiply this one by, let's use another colour. So the conjugate is exactly what we got there, except we changed that to a positive, right? So it's the square root of 2 times x plus h. Take 3, right? Here's the plus. Okay? On top of itself. Alright, so that's a little trick. Whenever we're doing first principles for a root, we have to multiply by the conjugate. We're multiplying by 1. We're not changing its value, we're just manipulating it at the top so we can collect like terms. And then what you have at the top, you've got a take b times a plus b. And so that just collects into a squared take b squared. And so you can go straight to that step. Right? Write that up there, write the conjugate up there, and then you're justified in going straight to that step. So the limit as h approaches 0 of a squared. That's going to be this component. Right? Square root on it, squared, it eliminates the square root. Okay, same with this one over here. And it's all on top of. So we've done the top times the top. This needs to come to the bottom now, doesn't it? We've got. And close that bracket. Okay, so then I'll expand the top. Alright, we can collect the top now. So we've got 2x take 2x, we've got minus 3 plus 3, we're left with 2h. Don't forget your limits. Okay, h is going to cancel, and that means in the next step we can apply the limit. So what are we doing? Effectively substituting h is 0. So we'll have, so once we apply the limit, we don't need to write it again. We've got Alright, so we're effectively putting h is 0 in there. So what does it simplify to? This. Now these are like terms, right? We've got the square root of 2x take 3 plus the square root of 2x take 3. We can add them together. And so that gives us 2 lots of All right, we've got one lot of it plus another lot of it. That gives us two lots of it. Two at the top, two at the bottom. Cancels. All right, so, but don't stop there. All right, there's a temptation to go, cracked it, solved it. Except it says we're interested in the slope at point A, right? So we found the slope function, but they want the slope at point A. So that means when x is 6, one on 3. All right, and hopefully you can see this one. So then you can go back and answer the conjecture part if you missed it already. So the conjecture part, you'd write k equals 1 on 3. But let's just make the case. So here, 0.3028, 0.3166, 0.332, 0.336. It's not the same because if you went 0.333, that's even closer to 1 on 3. And if you add on number 3 here, it's even closer, but they're not the same. They're not the same because this has an infinite number of them, right? Okay, so that's why they're not the same. All right, any questions about that one? Very good. Okay. Question 9, almost done. Almost done. All right. We've got, during a period when mask wearing was compulsory on public transport, a newspaper reported that only 75% of travellers obeyed the rule. A survey was conducted at this time, with only 4 carriages. One carriage was found to hold 45 people and 38 were wearing a mask. Another carriage held 55 people and 48 were wearing a mask. It is assumed that the choice the passenger makes in relation to mask wearing is independent of other passengers. Assuming that the newspaper article was correct, what's the probability of finding at least 38 people in carriage A wearing a mask? Alright, so this one's like a little bit tricky to sort of think about. What is it asking here? Assuming that the newspaper article was correct. So what part are they correct about? And the newspaper article has only made one claim. And that is that 75% of travellers obey the rule. Alright, 75% of travellers wear a mask. So that's their claim. We're given a p-value, right? And so then we're saying, what's the probability of at least 38 people in carriage A wearing a mask? So based off the newspaper article's claim. So in the carriage, right, there's 45 people, and we're saying, what's the probability of at least 38? So you've got 37, 38. It's the probability of this event, 38, 39, 40, 34, alright, all the way up to 45. Alright, because that satisfies the statement at least 38. And so this is a BCD calculation, right? Lower boundary 38, upper boundary 45, lower upper n is 45, and the probability of them wearing a mask is 0.75. Alright. So we evaluate that, we get 0.09. Alright, part 2. Find at most 48 people in carriage B wearing a mask. So in carriage B there were 55, and we're saying at most 55, we're saying at most 48, so that means 48 and down, right? At most 48, so 48 and down. So this is a BCD calculation, so that's part 1, here's part 2. The lower boundary, 0, upper boundary 48, out of 55, and 0.75. Alright, construct a confidence interval for the proportion of the population wearing a mask based on carriage A. So in carriage A, we're looking at the sample that's performed there, right? We have, and we want 95% confidence. Alright, so stat interval z first proportion. Okay, we're required for a proportion. We want 95% confidence, and we have in carriage A. In carriage A, we have 38 out of 45, and so that's the information we need for a distribution, a confidence interval, and we get from 0.739 to p to 0.844. Okay, does this confidence interval support the claim of the newspaper? Explain your answer. Yes, because the result lies in the confidence interval. Alright. Construct a 95% confidence interval for the proportion of the population wearing a mask based in carriage B. So in carriage B, 95% confidence interval, and in carriage B, we had 55 people, and we had 48 wearing a mask. Alright, so we calculate, that's the confidence interval we're doing now, so this is going to be C part 1, so that was B. So C part 1. And when you do the confidence interval, so again, just using your calculator, just changing those numbers, we're going to have 0.785 is less than P is less than 0.961. So true proportion lies somewhere in there for carriage B. Does this confidence interval support the claim of the newspaper? No, as 0.75 is below, completely below confidence interval. Alright. So carriage A supported it, carriage B didn't. And now they're saying, now we've got carriage C in another very crowded super spreader event. There were 72 travellers. How many of these people would need to be wearing masks to support the article at a 95% level of confidence? Alright, so there's two ways of answering this, and this is very similar to the test question we had about the toilet paper with the mullets. Yep. So what's going to support it? And so what we're doing is I think the simplest way, right, for it to be supported, we're going to generate a confidence interval with this information, right? We have 72 travellers, and we're going to change this. So let's just leave it blank for now, and we want confidence level 95. Now, the newspaper claim is 0.75. So if we keep changing this, like let's start with, I'm going to do it so I can write a distribution up so I didn't write any down. Let's start with 50. Alright, so interval Z first proportion. So let's start with 50, 72. Alright, so if I do 50, right, the confidence interval I get using x equals 50, the confidence interval I get is 0.588 is less than P is less than 0.8. Alright, so if I do 50, that supports the claim. Right, if I do 50, it supports the claim because 0.75 is inside, right? So then I'm going to say, all right, well, let's change it. We want to say, how many of these people would need to be wearing masks to support? Yeah, so it should say minimum, because I think there's two ways we can answer it, because that would satisfy it. We could say 50 people, but it should say minimum. And I think it wants to.
Question says minimum.
Yeah, the next question's an N calculation though, so yeah. Anyway, let's keep going here. So we've got 50 would support it, but we want to say what's the sort of the lowest amount that would support it. So then we might go, all right, well how about 45? And if I change it to 45, here's the confidence interval I get. 0.513 is less than P is less than 0.737. Alright, and that doesn't support the claim. That doesn't support the claim because the upper boundary is below 0.75. So if there were 45 people in the carriage, that's not enough. So it needs to be higher than 45. So we're going to go up above 45. Let's go for 47. Alright, 47 supports it. Alright, I've got the upper boundary is 0.76. And so what about 46? The question is, does 46 support it? And I've got 0.7498, which will be round. So 0.7498, 0.75. So it's supported. You need at least 46 people. At least 46 people to support it. Now, I don't know how much detail you guys want to go into because I think they've stuffed up this question in two regards. Because we've got here, that's sort of the minimum, right, 46, but there's also a maximum, because if too many people are wearing masks, then it's above the confidence interval at the other end. So let me show you what I mean. Like if we jump up here to 70, let's say out of 72 passengers, there was 70 wearing masks. All right, and if you do that confidence interval, look at the level we get of confidence. We get from 0.93 to 1. All right, and this is completely above the claim of 0.75. So there's two ways it could be wrong. You could be completely below it or completely above. So the question's a bit ambiguous. You can use trial and error. In the test, when we did it, if you look at my solutions, I've used a sort of algebraic process for it as well. If people are interested in that, I can go through it, but I think we might skip along a bit. Alright, so we've got one more carriage. Carriage D was investigated. Find the minimum number of people who would need to be in the carriage in order to construct a 95% confidence interval with a width no greater than 0.2. So I couldn't remember the formula for this one, but it's in 9E or 9F. We're doing an N calculation for P. So the formula is here it is. N equals 2 times 1.96 on top of W squared, P star, 1 take P star. Alright, or P hat. We use P star if we don't have a preliminary value. So that's the formula we're using. Now we're told a width of 0.2 squared. We're going to use the value 0.75 times 0.25. We're going to assume the newspaper article was correct. Alright, so if we do that, what do we get? Because I haven't done this one yet. 2 times 1.96 divided by 0.2 squared times 0.75 times 0.25. I've got 72.03, and we round up to guarantee that level of confidence, right? 73 people. You need to sample 73 people in order to have that confidence interval with a width no greater than 0.2. Very good. Last question. Okay. Now this question is a tricky one. I like it, but it is a tricky one. Okay, so let's read it carefully. The function a t to the b e to the negative ct, where t is greater than 0, models the concentration in milligrams per litre of a family of drugs t minutes after being administered to a patient. A, B and C are all positive constants that relate to a particular drug within the family of drugs. So it's like, right, efficacy of Panadol or Panadol type drugs and so forth. You're going to have some maximum variance. One example of a drug has values A equals 3, B equals 2, and C equals 0.5. On the following axes, sketch the graph for this drug. Show the coordinates of point X, where the concentration reaches a maximum, and the coordinates of Y, where the concentration of the drug is increasing at the greatest rate. Okay, so the function we're sketching, this is what they've given us, right? A, T, B, e minus ct, and we're given the numbers. A is 3. We've got B is 2, and we've got C is 0.5. Alright, so that's the function we're sketching. Alright, in your calculator. So I'll give you guys a minute to draw it up, and then I'm going to make a bit of an argument around it. So it's a surge function. It reaches some maximum level. Alright. And it wants us to graph, show the coordinates x, where the concentration is maximised. Alright, maximum concentration at this point in time. And the coordinates y. Y is the location where the drug is increasing at the greatest rate. So that means the coordinates at the point of inflection. So we can get that from our graph, right? Alright, so when is the rate maximised? At the point of inflection. So I might sketch the function and talk to you guys about that. So it's 3x squared e to the minus 0.5x. Alright, so here's our function, and we want to know when is it increasing at the greatest rate. That's when the point of inflection occurs. And so in order to determine that, point of inflection on f of x corresponds with turning points on f dash of x correspond with roots on f dash dash of x. So I can do something like this, right? I can go y equals that, hang on, what's the correct way to do it? Like this, f of x equals, so this, because I'm doing it on Desmos, f dash of x and f dash dash. So let me make that point clearly. So, point of inflection corresponds with the local max on the green function. Alright, the local max on the green function, which corresponds with the root on the purple function. Alright, so point of inflection on f of x is turning point on f dash of x is root on f dash dash of x. So that's when x is 1.172. We can mark that on your graph, point y. Alright, so it's about here somewhere for you. You've got a nice sketch of it. And really that question should be worth a few more marks because you have to sketch it and you have to label 2 points. I would say that's worth at least 4 marks. Okay, so next part. Alright, so here's where we're going to get a little bit tricky. Show algebraically that for this function, for the general function, not for the one that they're giving you with the values, the maximum time occurs at this value t. Alright. So if this is our function, so I'm going to make a long-winded argument here. At e to the minus ct. Local max occurs when f dash of t equals 0. Alright, that's always the case. Turning points occur when the first derivative equals 0. So that means we need to differentiate the function. Sorry, I'm missing a b there. So here we need to use the product rule. Alright, a is a number, but t is the variable, so that's going to be u, and e to the minus ct is a variable, so that's going to be v. Alright, so we have u and v. So for the product rule, a, t to b. Alright, we'll go through this one slowly so I can, So then for u dash, alright, when you differentiate x to the n, right, it goes to n x to the n take 1. So that same principle is going to apply here. We're going to have a as a number, that's hanging out, we're going to have a, the power comes down, b, t to the power of b take 1. The power of b goes down by 1. Alright, so that's u and u dash. V is a bit easier. And we'll smash all that together. Alright, so we've found f dash of t, and we want to find what are the values of t that make it equal to 0. So I'm going to put equals 0, and then we're going to perform some factorisation. U dash v plus uv dash. So looking along right, e is common, so we're going to pull e out the front. A is common, so we're going to pull a out the front. And we're also going to pull t to the b take 1 out the front. Alright, and I'm going to show you what that's going to look like. So I've said we're going to pull a, we're going to pull t, and e. That's what we're going to pull out. Most of those are okay. Maybe you're a bit unsure about this one, but let's justify it for you. So then we've got, what are we left with? Just b, take c, take tc. Alright, so the reason I've pulled t to the b take 1 out the front, right, if we're going to distribute that term, okay, we're going to get t to the b take 1 there, but if we distribute it here, if we do t to the b take 1 times t, we're going to get t to the b. Alright, so that's why we can pull it out the front, and now we're just going to apply the null factor rule, right? A does not equal 0, because A is a positive constant. E to the minus ct does not equal 0, because it's an exponential. So then null factor law, either t to the b take 1 equals 0, or b take tc equals 0. So this is a solution, alright, t to the b take 1 equals 0. That occurs when t is 0. Or, here we're going to have b equals tc, and t equals b on top of c. So that's the local max there. So there where the turning points occur, this one's going to be positive. Yeah, because b and c are both positive constants. Okay, the next one's a tiny bit easier. So, hence, show that the maximum concentration given by this drug is this here. So, this is the function, right? Here's the function, a t to the b, e to the negative ct. Now, we're told the maximum concentration occurs when t equals b on top of c. So that means, what's the y value? What's the y value that corresponds with it? So that's going to be a b on c to the power of b, e to the minus c times b on c. And we just got to process this a bit. Alright, so first one here, e to the minus c, so minus c on c. So see how you've got c at the top, c at the bottom, that cancels. And so what this is a, b on c to the b, e to the negative b. Alright, so I'm just going to make this argument slowly again. B on c to the b. E to the negative b is 1 on top of e to the b, right? Okay, which is 1 on top of e to the power of b. These have the same power, and so you can bring it into one bracket. Alright, so not all of those steps are required. Alright, now this is a hard one. This is probably the hardest question in the test this next part, and it's the last question. So we'll crack it, and then we'll be done. Another example of this drug reaches a maximum concentration of 0.5 milligrams per litre after 3 minutes and decreases to a concentration of 0.25 milligrams per litre after 4 minutes. Okay, so we're going to let's think about how can we answer this, and I've got a few ideas on how to explain it, but I think the first thing we want to do is write down all of the information we're presented with. So we have the maximum occurs when time is 3 minutes. And we also know from before that the maximum occurs when time is B on C. So we have B on C equals 3. That's the first thing we've got. Alright, the second thing is we've got, and it doesn't matter if you use the maximum or if you use the original function, right? So this is the maximum, okay? And this is the maximum, and we're told the maximum, A, B on C, E to the power of B, we're told the maximum is 0.5. Alright, that's what the maximum is. And then lastly, after 4 minutes, so that's when time is 4, the concentration is 0.25. So that means when you put 4 into this equation, the y value is 0.25. So let's write, so we've got 3 pieces of information, 1, 2, and here's the third one, when time is 4. So we're going to have A, 4 to the B, e to the negative 4c equals 0.25. Okay, so the first thing is to get all the information out, and now you go, how can I combine these to solve for B and C? They only tell you to solve for B and C, which means you're not really interested in A. A is going to get eliminated somehow. So maybe there's a little bit of a clue in itself as well. And we can do, like, if you're looking at it, probably you're looking at, I've got B on C equals 3. This tells you a couple of things. Firstly, we can express it in terms of one variable. And the other thing is, wherever we have B on C, there we've got B on C, that could be written as 3, right? So this term could be simplified to A, 3 on top of E to the power of B equals 0.5. So we could do that, that's okay. Alright, so maybe we got 2 marks there possibly. Alright, so I think here's the trick. I think here's what we're sort of looking at. 0.5 and 0.25. How can we equate these? Because if we can equate them, then we can eliminate A. And what we need to do is double this one. If you double 0.25, you get 0.5, right? And so that means 2a times 4 to the b e to the minus 4c equals 0.5. And now, because they're both equal to 0.5, this component equals this component. Alright, so let's write that out. We've got, this is a mess, isn't it? A, 3 on e to the power of b equals 2a, 4 to the b, e to the minus 4c. Alright, and you don't really have much further to go. Alright, we want to express it in terms of one variable, okay, because we want to solve for one variable to start with, and then we've got this relationship. So because we've got b equals 3c, we can either change this over here, or we can change the b's to be in terms of c. Doesn't matter. Let's go with substituting b for 3c. Alright? So we're going to have a times 3 on e to the power of 3c. Alright, I'm just changing the b to 3c. Alright, so now it's in terms of one variable. It's all in terms of c. Well, the other thing, of course, is a is on both sides. I said we'd eliminate that, so we divide both sides by a. And there's a temptation here to really try and simplify it and bring it together. But you're going to be pretty hard pressed to do it. You can see we've got 3c on both sides, so one thing you could do is move the 4 over. So like, I'll explain how I was trying to manipulate this a little bit last night. So one thing I was thinking is, 2 and 4, they could be expressed with the same base, right? I could do something like this. Times 3c, yep. That would be correct. 2 to the 2 times 3c, right? That there, and then here this is just hanging out. And now they have the same base. I could add the powers together. So this could be expressed something like this. All right, and I was just processing it and crunching it and trying to think, how am I going to crack this? Okay, so then over here we've got 3 on E, 3 to the C. But it doesn't really matter how much more you process it, because ultimately you do have to just G-solve this point of intersection. All right, there's no neat solution. Where it can get a little bit neater is, so you, like I was going down that route and I wasn't very successful, is if we divide both sides by 4 to the power of 3c, right, what we're going to have is 3 on E to the 3c times 1 on 4 to the 3c, and you can bring those together, so then you've sort of eliminated one of the c's. So what's that give you? That's giving you 3 on top of E, 4e to the 3c. Alright, so it's taking it a little bit closer. But anyway, here's how we're going to solve it. We're going to put this in equation solver. Alright, so we've got 3 on 4e to the 3c equals 2e to the minus 4c. So you can do it in equation solver, you can do it as a graph. Alright, c is our variable. Alright, and I did that and I got c equals 5.06. Alright, c is 5.06, which means b is 3 times c. So b has to be 15.18. Alright, and it wouldn't have mattered if you solved for b or c because they're directly proportional, right? You can obtain one from the other. So that is a pretty hard question, that last one. Alright. But hopefully most of the exam was pretty good. Hopefully we feel alright about it, so that's why a little bit longer than last time. But remember the exam, I mean I'm up here explaining it, so that takes longer. But the exam is 2 hours and 10 minutes, so you've still got 20 minutes reading time, and we've answered everything, right? We've gone through, we've answered everything. Yeah, excellent. So I'll stop there. If any questions you want anything printed, hang around and let me know. Otherwise, trial exams